So let us start normal subgroups. So this lecture is a part one of this normal subgroups lecture. So before talk on normal subgroups, I would like to discuss what are normal subgroups in a group theory. So to understand the normal subgroups, we have to understand about the subgroups. So consider one subgroup whose name is H of group G. Now, for the sake of simplicity, I would like to take this H containing 3 elements. No doubt it may contain more than 3 elements, but for understanding, we are considering H containing 3 elements. Suppose H1, H2, and H3. All right. Since capital H is a subgroup of G, that means H is a subset of G. So therefore, the elements in capital H, these are H1, H2, H3, which are member of H, are also member of G. So now take any element from a group G. So let X belongs to this group G. Now what I should do with this element and this set? So just multiply to the set H by X from the right side. The meaning of multiplication of any set and any element is nothing but you multiply all the elements of set H by X from the right side. And that's why in this set I am getting H1X, H2X, and H3X. Now also multiply to this set H by the same element X from the left side of H. Therefore, we are getting XH, and the meaning of the multiplication is you multiply to all the elements of H by X from the left side. So we can get XH1, XH2, and XH3. Since HX1 and H1X are the members of group G, and G is the only group. We don't know whether it is a abelian group or not. So we can't write XH1 is equal to H1X, because we can write only when if we know G is a group, abelian group. So we don't know whether the G is abelian or not, therefore we cannot write XH1 is equal to H1X, XH2 is equal to H2X, and XH3 is equal to H3X. So these 6 elements, they must be equal when G is abelian. But when G is not abelian, then they may be equal or may not be equal. But with abelian property of G, if these elements are equal, then we may write Hx is equal to Xh. Now, this beautiful observation noticed by the great mathematician Galois. He noticed such a cosets and he put remarks on a subgroup H. That is, H would be a special subgroup of G who made possible Hx is equal to Xh. And this special subgroup is called as normal subgroup of a group G. So in short, we may say that a subgroup H such that its a left coset and its a right coset in G are equal, then that subgroup who made this possible, Hx is equal to Xh, that subgroup is called as a normal subgroup of a G. So this is a concept of normal subgroups. Any subgroup made cosets, left coset, right cosets, but there is no guarantee that these left coset and right cosets are equal. But a subgroup which will give left coset is equal to right coset, that particular subgroup is called as normal subgroup of G. Now suppose N is a normal subgroup of G. N is a normal subgroup of group G. Now consider one element, small g belongs to this capital G. Now since N is a normal subgroup, that means the left coset of N in G is equal to right coset of N in G. Therefore, we may write this right coset Ng is equal to left coset Gn. Now, since this G is a member of group and therefore this inverse of this G must present in the group G. And therefore, we can multiply G inverse to this equation from the right side. Therefore, we are getting N G into G inverse is equal to G and G inverse. We know that G and G inverse after multiplication it will give identity, and therefore we can write this as N into E is equal to G and G inverse. Now the multiplication by identity according to identity law, it is N is equal to G and G inverse. So we may define that if N is a subgroup of G such that that subgroup will satisfy this condition, N is equal to G and G inverse for all G belongs to G, then this subgroup N is called as normal subgroup of G. So we may get another definition of normal subgroup. A subgroup N of G which satisfy N is equal to G into N into G inverse for all G belongs to G, then this N is called as a normal subgroup of G. Now, suppose to elaborate this, now I am considering this N containing 3 elements for the sake of simplicity, N1, N2 and N3. These are the elements of this N. Now, I would like to construct this set G and G inverse. So I am multiplying G from the left and G inverse from the right. So I will get G and G inverse is equal to G n1 G inverse, G n2 G inverse, and the third element is G n3 G inverse. Now if you observe all the elements of this set, and we know that since n is a normal subgroup, this G and G inverse is equal to n. That means all these three elements are member of n, and therefore we may write, instead of separately writing all the three elements, I may write G and G inverse belongs to n, and this small n means for all n belongs to n. That means n may take the value as a n1, n2, n3. And now this is also condition which elaborate the normal subgroup. That's why we may define n is a subgroup of G such that G and G inverse belongs to n for all n belongs to G and for all G belongs to G. Then this n is called as a normal subgroup, and that's why now we are ready to define normal subgroup using this. So in the definition of normal subgroups, we put this condition and then we will proceed. So let us define normal subgroups. So how we can define normal subgroup of G? So for the definition, we may write, if n is a subgroup of G, and n is said to be normal subgroup of G, if G and G inverse belongs to n for all n belongs to n and for all G belongs to G. The meaning of the definition is you take any member of group G, so that will be denoted by small g. The meaning is not that it is only one member. You can take any member from G. Put here from the into the left. You take any element from the capital N denoted by small n, and then the inverse of this element multiply from the right, and the product of all these three elements will become member of n. Then only this n is called as a normal subgroup of G. So for understanding, you may take element from G as identity. So you write identity here, you write any element from the n, you write inverse of this left element, that is E inverse, and this is equal to n, and n is a member of n. Therefore and it is satisfied by only one element, that is identity, and it would be satisfied for all the elements of G. Then only this n is called as a normal subgroup of G. So this is a definition, and we are using this definition to prove next some lemmas and theorems. So let us see one lemma. Prove that n is a normal subgroup of G if and only if G capital N G inverse is equal to n for every G belongs to G. Now in this theorem, if we read the statement of the lemma, there is a if and only if. Its meaning is, first suppose that n is a normal subgroup of G. I would like to make correction here. It is not a small n, this is a capital N. Okay, this is a capital N. So prove that this capital N is a normal subgroup of G. That means you first suppose N is a normal subgroup of G and then prove that this condition. And conversely, suppose that G and G inverse equal to N for every G belongs to G. And using this condition, we have to show that this capital N is a normal subgroup of G. So this is the meaning of the lemma, and in this lemma, we will prove these two statements biconditionally. So to prove one thing, so suppose that so I am here proving this lemma. Suppose that G and G inverse is equal to capital N for all G belongs to G. I am supposing this statement. Now, if you observe this is a set, left side is also set, and both sets are equal. When the two sets are equal, it is only possible when these two sets are subsets of each other, so that we know. And therefore, our conclusion from this equality, that is G and G inverse, that is a set from the left side, is a subset of this N, as well as N is a subset of G and G inverse. But I am considering only one case. G and G inverse is a subset of N. What is its meaning? Meaning is when this G and G inverse is a subset of N, its meaning is every element in G and G inverse is member of N, because G and G inverse is a subset of N. Now, this is a set, that's why I am considering a particular element G, and the element from the N denoted by small n G inverse belongs to N. And this is true for every element of capital N and every element G from G. So this is true for all G belongs to G, and for small n belongs to capital N. And if you observe that, what is this? This is the condition in the definition of normal subgroup, and hence it is satisfied according to definition of normal subgroups, and hence by definition of normal subgroups, which we have stated earlier, N is a normal subgroup of G. So this part we have proved. Now we'll prove converse part. So now we will suppose now N is a normal subgroup of G, and we have to show that this is equal to N. So now conversely, suppose that N is normal subgroup of G. Once we suppose that N is a normal subgroup of G, according to definition of normal subgroups, G and G inverse belongs to N for all G belongs to G and small n belongs to N. This is from the definition of normal subgroups. All right. Now these are the elements of the set G capital and G inverse, and therefore every element is a member of N. That means that G capital and G inverse is a subset of N. Let me call this expression is an equation number 1, because we want to show that these two sets are equal, and this is possible only when we have to prove that this is a subset of N and N is a subset of G and G inverse. So first what we have proved that G capital N G inverse is a subset of capital N. Now only we have to show that N is a subset of G inverse. So whatever we want to show that I am putting here in the form of claim. Claim is to show that N is a subset of G and G inverse. We want to show that this now. Now the question arises how to show that this N is a subset of G and G inverse. So we know that from the equation 1, what equation 1 gives knowledge us, that is you take any element from G or write capital N and take the inverse of this element, that would be a subset of capital N. So using the fact of this relation from equation 1, since G is a group, so if G belongs to G and G is a group, implies that G inverse is also a member of G according to inverse law. So according to the fact, I can take any element from group G. So here particularly I am considering this element to satisfy this. So I am considering one element from G, that is nothing but G inverse. Then I will write capital N, and then I will write the inverse of this left element, that is G inverse inverse, and this is a subset of what? N. We know that inverse of inverse is original element, therefore we can write this as a G inverse capital N. G is a subset of capital N. All right. Now, as we have taken one element from G, that is G inverse. So G is a group. So we may take another element from G, and identity element must present in G because G is a group. Therefore, instead of taking any another element from G, I can take identity element from G. And therefore, particularly if I will take E, so since I will write here, since G is a group, therefore the identity element belongs to G, and therefore we can write N is equal to that E N E. Now instead of this E, I will write G into G inverse, keep this N as it is, and instead of this E, again I will write G into G inverse. Now I will write this expression as G inverse capital N G, and this G inverse here. I can change the bracket. Why I am changing this bracket? The rule is which I am applying here, that is associative law. You can give the reason associative law. Now we know that already from the last slide we have proved that G inverse NG is a subset of N. Therefore, this capital N is a subset of G. Here instead of G inverse NG, I will put N, and here G inverse. Now let me call this expression is an equation number 2. And this is possible due to the previous result here. Here we have proved that this one, I am using this step here. And therefore from equation 1 and 2, in 1, G and G inverse is a subset of N. In equation 2, N is a subset of G and G inverse. Therefore from equation 1 and 2, we may write as a G and G inverse is equal to N. And therefore this is what we want to prove. And hence when N is a normal subgroup of G, G and G inverse is equal to n. And this is the end of the proof of this theorem or this lemma. Now we want to see another lemma, and which is very important. Prove that n is a normal subgroup of G if and only if every left coset of n in G is also a right coset of n in G. Again, here n is not a small, it is a subgroup, therefore it is capital. So it is capital N in G. So in this lemma, again the statement involving if and only if. That means, first of all, we have to suppose that n is a normal subgroup of G, and then using the definition of normal subgroup, we have to show that left coset of n in G is equal to right coset of n in G. And conversely, suppose that left coset and right coset are equal, and using the fact, we have to show that n is a normal subgroup of G. So let us start the proof of this lemma. So first of all, suppose that n is normal subgroup of G. Normal subgroup of G. Now once we suppose that n is a normal subgroup of G, we may use the definition of normal subgroup, or we may take the result from the previous lemma. In the previous lemma, we have proved that when n is a normal subgroup, then G capital N G inverse is equal to n. So here we want to show that result related to right coset and left coset. Therefore, instead of taking element from the definition, I can use the result that is a previous lemma. And therefore, I am using that result. Therefore, we must mention that we know that from the previous lemma, n is normal subgroup. N is normal subgroup if and only if G capital N G inverse is equal to n. Already we have supposed that n is the normal subgroup of G, and according to this previous lemma, we may write G capital N G inverse is equal to capital N. Now I wish to cancel out this element G inverse, and therefore I have to multiply G from the right side. So you may write multiplying G both sides from the right. So you can write G and G inverse into G is equal to N into G. We know that G inverse into G is the identity element, therefore it is G N E is equal to N into G. The identity element never effect as a product, therefore we can write G N is equal to N into G. And if you observe that this is a left coset of N in G and this is a right coset of N in G, and that we want to show. And therefore, when N is a normal subgroup, we have proved that left coset of N in G is equal to right coset of N in G. So we proved first part. Now let's prove that second part. So that's why conversely, suppose that what we want to suppose, the left coset of N in G is equal to right coset of N in G. So that means you are writing N left coset means G N is equal to N G. But here the question arises, why you are taking G element in both the cosets for constructing left and right coset. You have suppose only the left coset of n in G is equal to right coset of n in G. Therefore, left coset created by some another element may be equal to right coset of n created by another element. Therefore, first of all, we never have to consider this step. We are just stick with this condition, that is the left coset of n in G is equal to right coset of n in G. So what I will do here, I am considering two different elements. Let x and y belongs to G such that x is not equal to y. And now, using these two elements, I will construct one is a left coset and another is a right coset. So suppose that using x I am constructing right coset, so this is nx. Using y I am constructing left coset, this is yn, and according to this condition I am supposing these are equal. Let me call this expression is an equation number 1. Now, you have taken x and y are the members of G. G is a group. So you may take any element from the G, and G is a group. That's why we have the guarantee that the G containing identity element. So now, since instead of x, y, if I will take since identity element from G, then what happened? This y into E, according to identity law, its answer is y, and this belongs to, so instead of G, I will take E identity element from N, not from G, from N. So now this y into E is nothing but y is a member of NE. NE is nothing but N, and therefore this something went wrong. So you cut this. So take element E from N. Therefore, this implies y into E belongs to y into capital N, because this E is a member of N. But y into E is nothing but y according to identity law. Therefore, y belongs to what? Y into N. Alright, here y into N. And from equation 1, y into N is nothing but nx. So this implies y belongs to nx from equation 1. Alright. But we know that y is but y belongs to ny, because n is a subgroup, n containing identity element, and this y when multiplied to that identity element, this coset containing y. We have the guarantee. That's why y belongs to what? Ny. Now this y belongs to nx means right coset nx, and this same y belongs to right coset ny. That means this y is common in two different right cosets. We know that two right cosets of n in G are either equal or disjoint. That means if two right cosets are identically equal, that means all the elements of the two right cosets are same or totally different. That means there is no possibility to have only one element in common between these two right cosets. So I am observing that y is a single element which is common in this right coset and this right coset, and when this is one is common, then nx, this right coset, and ny both are equal. So it means no single element is common between any two right cosets, and if it is possible, That means one single element we are observing that common in both right cosets, it include that nx is nothing but equal to what? Ny. Now I will put this result, because already we assumed that here nx is equal to yn, and now we have proved that nx is equal to ny. So instead of nx, I'll write ny. Therefore, from equation 1, this is instead of nx, I am writing ny. This is right side of equation 1, that is yn, where y is a member of G. Already we have taken from G. And therefore, this is the left coset, this is the right coset, and this is the left coset created by the same element y. I am considering these are the equal. Now what I should do, multiply both sides from the right side by y inverse. So I will write n into y inverse is equal to y and y inverse for all y belongs to G. This y into y inverse is identity, therefore n into e is equal to y and y inverse for all y belongs to G. The identity, according to identity law, this is equal to n is equal to y and y inverse for all y belongs to G. And this is, the definition of the normal subgroup or criteria from the previous lemma, and therefore we may say that therefore capital N is a normal subgroup. So in this lemma we have proved that when n is a normal subgroup of G, then every left coset of n is equal to right coset of n in G, and conversely, after supposing every left coset of n in G equal to right coset of n in G, we have proved that n is a normal subgroup of G. So this is the end of this lemma also. Now we'll see another lemma. Prove that capital N is a normal subgroup of G if and only if the product of two right cosets of n in G is again a right coset of n in G. So again, in this theorem, the statement involving if and only if, that's why first of all I'll suppose n is a normal subgroup of G. So begin proof. Suppose that n is a normal subgroup of G. Once we suppose that n is a normal subgroup of G, we may write according to definition G small n G inverse belongs to n, or according to first lemma G capital N G inverse is equal to n, or by previous lemma we may write left coset of n in G is equal to right coset of n in G. Right? But what we want to show that product of two right cosets of n in G is again a right coset of n in G. That's why we need two right cosets, and to create right cosets we need two elements from group G. So let A and B, these are the two elements from group G. Therefore NA and NB are two right cosets of n in G. Now we want to show that the product of these two right cosets NA and NB is again a right coset of n in G. But you know that n is a normal subgroup, and we are considering this NA is a right coset, and already we have proved that when n is a normal, you may state here, we know that n is a normal subgroup of G, then every left coset of n in G is equal to right coset of n in G. Therefore, we can write NA is equal to AN and NB is equal to BN according to previous lemma. Now, what is our claim? Now, claim is to show that product of two right coset, that is product of NA and NB, is again right coset. All right. So now I'm considering the product NA into NB. Now I'll write this as a N. I'll put bracket here. You must know why I'm putting bracket here, because N is a subgroup. It is a normal subgroup. A, B are the elements from G. G is a group. Therefore, we can enjoy the property of associative law. So we can write this as by associative law. Now continuing this step, now inside the bracket I am observing A into N, and we know that A into N is equal to NA. Therefore, you can write this as NA into B. Now again, using the associative law, we can write this as N into N in one bracket and A into B in another bracket. And we know that set N into set N is nothing but N, and this is AB. Now this looks like a right coset, but the only problem is what is this element, whether this is a member of G or not. If we prove that A into B is a member of G, that means N into member of G create a right coset of N in G. Now how we clarify that the A into B is a member of G? Already we know that A and B both are members of G. G is a group. It must satisfy four conditions. The first condition is a closure property. Therefore, according to the closure property in G, A comma B belongs to G implies AB belongs to G. And hence this AB belongs to G, this NA is right coset of N in G. And therefore, we have proved that product of two right cosets is equal to, again, a right coset of N in G. Now, we would like to show that it's a converse part, and in the converse part, we are assuming that the product of two right cosets of N in G is again a right coset of N in G, and our claim is to show that capital N is a normal subgroup of G. So conversely, suppose that product of two right cosets of N in G, right cosets of N in G is again right coset of N in G. I am supposing this statement. Now our claim is to show that N is normal subgroup. To show that N is a normal subgroup, we have to show that any one condition, that is the G and G inverse belongs to N, or G capital N G inverse is equal to capital N, or left coset is equal to right coset. From either these three statements, we may conclude that N is a normal subgroup. So now, the product of two right cosets of N in G is again a right coset of G. So now I am considering one element. Let G belongs to G. Since G is a group, the inverse of G is also a member of G according to inverse law. Now, we have two elements from the G. One is a small g and another is its inverse. So we may construct two right cosets using these two elements. So therefore, Ng and Ng inverse are two right cosets, because to construct right cosets we need only two elements from the G. One is, I have taken G and another is G inverse. So Ng and Ng inverse are two right cosets of N in G. And already we assume that the product of two right cosets is again right coset. Therefore, I'll write by hypothesis, by assumption, or by hypothesis, this right coset multiplied by this right coset is again a right coset of N in G. So if you multiply this, is again a right coset of H in G. Now, who is this N? N is a normal subgroup. That means it is a subgroup. That means the identity element present in N. So since N is a subgroup of G, no doubt it is a normal subgroup. No, it is not a normal subgroup. It is only subgroup. We want to show that N is a normal subgroup. So N is a subgroup of G. This implies identity element must present in the subgroup, that is E belongs to N. So now this is a N and I am considering one element from the N. Therefore, we may write E, that is a member of N, into G, again E, member of N, again G inverse. This element belongs to N, G inverse. According to identity and inverse law, the product of these four elements is nothing but E. Therefore, E is also belongs to Ng inverse. All right. So what will be the next step? The next step is how we want to show that two right cosets, this is also right coset containing E, and one more coset, that H itself is also containing E. So we know that HE, that is H, sorry, not H, this is NE equal to N, is also right coset of N in G containing element E. So this right coset containing E as well as this right coset also containing E. That means one element E common in both the right cosets, and we know that once we got one element common in both the right cosets, these two right cosets must be identical. Therefore, using that fact, I can write this Ng inverse. This right coset must be identical with this right coset for all G belongs to G. Now I am considering one element from this coset. So for this purpose, I will take some elements from the N, that is suppose N1, G, another element from N, that is N2, G inverse belongs to capital N. For some N1, N2 belongs to N. N is a subgroup All right. Now I will multiply by n1 inverse to this expression. So I will write n1 inverse, this n1 g n2 g inverse belongs to n1 inverse into n. But since n is a subgroup, n1 belongs to n, therefore its inverse is also belongs to n. That means this n1 inverse is a member of n. And when the element of n multiplied to n, I will get again n. Therefore, multiplication of these two elements is E, G, and 2 G inverse belongs to this product is nothing but capital N. According to identity law, I will get G N2 G inverse belongs to N. And we know that N2 is the element of N. Therefore, now I am taking into, now you can take any other element from N. Therefore, in general, we can write G N G inverse belongs to N for all N belongs to N. And G is also belongs to G. And this is a definition of normal subgroup. Therefore, we may state that N is a normal subgroup of G. So now we have proved this lemma also. Now, lastly, in this part, we will prove this theorem, prove that intersection of two normal subgroup is again a normal subgroup of G. So if we read carefully this theorem, statement of the theorem, we want to show that intersection of two normal subgroups is again a normal subgroup. And for this purpose, we need two normal subgroups. So let N1 and N2 be normal subgroups of G. That means according to definition, G, any element of N1 into G inverse belongs to N1. Similarly happens with N2. Now what is our claim? Claim is to show that the intersection of these two subgroups, that is N1 intersection N2, is a normal subgroup of G. Normal subgroup of G. We know that to become a normal subgroup of G, whoever want to become normal subgroup, that must be a subgroup of G. So that means first we have to show that N1 intersection N2 is a subgroup of G. But this is created by this N1 and N2 and both are separately normal subgroup of G, means obviously they are subgroups of G. And we know that the theorem from subgroup section, intersection of two subgroups is again a subgroup of G. So since N1 is a normal subgroup, therefore N1 is a subgroup of G, N2 is a normal subgroup, therefore N2 is also a subgroup of G, and we know that intersection of two subgroup is a subgroup, therefore N1 intersection N2 is a subgroup of G. Okay, we have done this subgroup of G. Now only we have to show that this N1 intersection N2, which is a subgroup of G, is nothing but a normal subgroup of G. For this purpose, we have to take one element from this subgroup. So let N belongs to N1 intersection N2. The N is a member of intersection, therefore we can imply that this N belongs to N1 and N belongs to N2 because of the intersection. But N1 is already normal subgroup. So this implies that G N G inverse belongs to N1 and G N G inverse belongs to N2. And the reason is N1 and N2 are normal subgroups. That's why this is happening. That means the same element G and G inverse belongs to N1 and N2. That means G and G inverse belongs to N1 intersection N2. For all G belongs to G and N belongs to N1 intersection N2. And what is this? This is a definition of normal subgroup, and it has been satisfied by N1 intersection N2. Hence, we can say that N1 intersection N2 is a subgroup of G. So therefore, we conclude that hence, by definition of normal subgroup, N1 intersection N2 is normal subgroup of G. So this is the end of this theorem. So thank you very much for listening some lemmas and some theorems on normal subgroups.